this computer. Hello again, I'm Dr. David Ehrman. I'm going to be your lecturer for this series here. You should receive that email every Monday morning on what's due this week. It'll have the new Zoom code. If we have a quiz or an exam that week, that'll be on there. If we have homework due, that'll be on there. And I plan to have several in-class activities where we can actually get together, break out into small breakout rooms, and then you can do kind of peer-to-peer talking. And so, like, you know, how do we attack this problem, et cetera. Okay. So then we're also going to have our book and homework and exams are all going to be on Top Hat. I've heard some horrible stories about Examity and some other testing platforms. I have had very good success with Top Hat. Once we set up our settings the first time, I've had maybe 1 or 2 students per exam not be able to successfully get in on time, right when they're supposed to, and successfully complete the exam. So I have a really high hope that you will have a very low stress testing and quizzing through this Top Hat platform. Okay. In addition to that, I worked with Top Hat over the entire summer to reorganize the book that they had online so it kind of follows what Solomon's was. And if you've already bought Solomon's, email me. I have some ways around, you know, the Top Hat issue that you might have, but just email me on that. But I find that Top Hat is going to be really great for this distance learning. You can read on your own, and if you'll notice on the book, in the reading assignments, every couple paragraphs, there's a question. And so this is a self-test question. This is not graded. This is low, you know, stress. Answer the question. You can try it as many times as you want. And so that kind of gets you to every couple paragraphs, say, do I really understand this? Do I really understand this? And then, so that's where I think the Top Hat platform gives us an opportunity to do this really, you know, spontaneous learning, spontaneous reassessment, self-assessment each time we do it. And so I think that gives us an opportunity we don't have with other books. And so that's a really good thing. The exams are going to be very similar to what the homework is. They're going to be same style of question, same wording of question. So again, the testing should be very familiar. It shouldn't be, you know, well, you know, he does all this, you know, and then these are questions worded very weirdly now. And so that shouldn't happen with our quizzes and our homeworks and our exams. So we should see that. The slides on Top Hat aren't complete yet. I'm still working on paring them down and making them pretty and making them look like they come from Texas State. And you'll see that in the slides I go over later today, is that I'll be updating the slides, and I'll have 2 sets of slides on Top Hat by next week. There'll be what I call the student set, which has blanks in it. And so if you're following along, you can annotate as you go and follow the blanks. And then there's also the full set, which has everything correctly worded, correctly spelled. Occasionally I misspell things. And so you can go back and double check your spelling and such like that. So that's what we're going to see with our Top Hat system. The material itself follows the exact same procedure that everybody else, you know, that was in Solomon's and other books, and it follows the ACS exam schedule. Although we will not be taking the ACS exam this year because of the distance learning. When we do all get back into a physical classroom, we'll go back to those ACS, and you'll be fully prepared for that ACS exam. So the American Chemical Society exam. So let's see, that is the primary how to look at the things due this week. The second thing I want to talk about is some things about success in an online learning environment. Okay, so from what I've been able to learn over the last few semesters, I taught all summer and taught multiple classes, and so I've you know, been pinging students about what works and what doesn't. And so one of the things that's different about online learning than your standard lecture is that you actually have to be more organized, okay? You have to kind of set aside time to read ahead of the lecture. You have to set aside that time and know when your due dates are, okay? So there's a little bit more of an upfront planning on your part to make it successful. But overall, the information is usually disseminated, and we're going to give you opportunities to ask each other things in a peer-to-peer kind of way. In my in-class breakout sessions, we have our SI system, and Nicholas will talk about that in a little bit. And that also gives an opportunity for different kind of problem sets. And then once a week, I'm going to try to break out a little bit of time that we look at how to attack problems, okay? So we want to do the synthesis, how to attack a problem. We want to figure out how do we link all these different reactions together. I have a plan, I have a little exercise that you can do to help link all those things together. How do we learn all the different functional groups? We're going to be doing that in our second module. And so I'm literally going to have flashcards for you to figure out all the different functional groups and what to look for in the different functional groups. So it is going to be a little bit more on the front end planning side, but overall, the net result will be a hopefully positive learning experience. And you're going to learn a lot and be able to still have an opportunity to do a little bit of that one-on-one with me, one-on-one with the SI, one-on-one with each other. So that's a beginning of that. Hey, we're up to 36. That's great. Nicholas, are you prepared? Because I will allow you to, let's see, I need to give you sharing. Here we are. Or make co-host. So I'm making you co-host now, so you can go ahead and share your slides.
Sure, I'll do it in a second. So hi everyone, my name is Nick. I'm going to be your SI this semester. A little bit about me, I'm a biochemistry major, biology minor, communication studies minor. This is my first time being an SI. I took organic chemistry 1 in the spring, and as you all know, that was a little wild. We were all pushed online, and then in June, I took organic chemistry 2. That is all to say that I have some experience with organic chemistry online, and yes, it's going to be very hard, but I'm here to say it's doable. And I really like the class, so I'm excited to teach it all to you guys outside of the lecture. And now I guess we can talk about what SI is, considering you guys are all in Organic Chemistry 1, you have some experience with SI, but just in case you're a transfer student or something like that, Supplemental Instruction is what SI stands for. I am your SI leader. We will be doing 50-minute weekly study sessions to just continuously reinforce what we learn in lecture, because that is very important. Doing a little bit of organic chemistry every day goes a long way. Every week I'll be planning activities. They're not necessarily as serious, they're fun, they're supposed to be engaging and as social as we can get online. This is called a weekly course assignment. That is what we refer to the SI sessions. You have to attend 1 SI session a week or 10 before November 9th. And the reason we push this and it's required is because it actually works. This is the statistics for the spring semester. Students who regularly attend on average receive a final grade 1 to 1/2 to a whole letter grade higher than students who do not regularly attend SI sessions. The blue is people who got A's, B's, and C's. So 10 to 14 sessions attended, they're averaging a 96. Compared to the orange, which is people who got a D, F, or withdrawal rate, and that's 4%. So it's an interesting little graphic for you guys to show that it does really work. And now we can talk about how you're going to be scheduling your SI session that you're going to attend. SI has created a Qualtrics survey where you take this survey. It's very quick. It opens at 7 p.m. on August 25th, which is on Tuesday, and it will stay open until 11:55 p.m. on August 27th or Thursday night. Like I said, it's a very quick survey. It will show my 4 sessions that I'm offering every week. You will be choosing based off of your availability the session that you were most likely willing to attend. And on Friday, the SI administration will get back to you and show you the session that you matched with. And I believe that's everything I had to say about Qualtrics. But if there are any questions, feel free to email me. I'm really good with emails. I usually get back the same day, if not the next morning. So I can stop sharing. Oh, very important last thing is this survey is a first come, first served basis. Once a session has enough students that signed up for it, it will be closed. So try to fill this out at 7 p.m. on August 25th, just so you can have the most options to choose from when it comes to your session plan. So I will stop sharing. Thank you very much for your time. I'm looking forward to seeing you all next week when sessions start.
Okay, before we go any further, does anybody have any questions about SI or about this online kind of learning before we get too far along? I have it so you can unmute yourself and go ahead and ask questions. There's also the Zoom chat. If you are a little shy, you can just type in the chat. So, well, okay. Well, you're figuring out if you want to do something in the chat room there. Let me go ahead and share one thing real quick. It's related to the SI. It is, there we go, share. Okay, so if you go to the Canvas site, there is both a PDF version and an online version for our syllabus. It goes through a lot of different things like, penalties for Zoom bombing, et cetera, like that. But the SI participation is 5% of your grade. It is amortized, which means if you make all 10 sessions, you get 5%, or the 100% of the 5% added to your grade. If you only go to 9 sessions, that's 4.5%. So it is amortized. So if you miss one, it's not super critical. Just keep going, because from my experience, these SI sessions do help increase your grade. It gives you an opportunity to do this low stress asking of questions and getting other people's perspectives. My perspective on organic chemistry might not be, you might not understand it very well, but talking to other students, talking to the SI is a good way to get a different perspective and learn that concept, okay? And learning those concepts, and building on those is very important. So I do amortize for that. Homework and team activities are two more things that are kind of low stress, give you an opportunity to be active in both, with homework, it's something that you're kind of doing yourself as a self-check before exams, but with team activities, it's something you can share and work together. And most of the team activity, about half the grade is just participation. The other half the grade is getting the question right. Okay, so those are, that's why the team activity is such a good opportunity to learn, make mistakes, and learn from those mistakes. And so it's really a good opportunity to do that. Okay, I'm going to stop sharing. All right. Anybody have any questions about the administration of the class or anything we're going to do? Okay. So I do have these live sessions for 3 times a week. I'm planning on having all exams scheduled on Fridays so that we have our Fridays from 10 to 10:50. So there'll be 50-minute exams and there'll be multiple choice and they'll be on top hat. So that way, you can relax for the weekend. So since all the SI sessions are scheduled, Monday through Thursday, I believe, that'll give you an opportunity to ask questions about that test before it happens. So also, all homework, I believe in this class is due on Thursday at midnight. The reason I do that is so that as soon as midnight passes, you can review your homework for things you got right and things you got wrong on Friday morning and use that as a study tool to help you study for the any quiz or any of the exams. Okay, so any questions about any of that?
On the email you sent out for this morning, it said that the homework would be due on Friday for this week. Is that just for this week, or was that like
for this week? Because we don't have an exam this week.
Okay, just making sure.
Yeah. What I will do is on weeks we do have exams, homework will be due the Thursday before. And I have 4 planned plus the final. So And I will put those on the schedule by the end of the week. Good question. Okay. And by the way, we are a small enough group here. I mean, we only have 43 people in the class, so the opportunity to unmute yourself and ask a question, I am perfectly happy with that. It's not like we have 300 people, so I think that gives us, our class size gives us an opportunity to do this. But again, Zoom chat I have open, and so what you'll see when I first start sharing stuff is I'll start looking off screen because I'm going to move the gallery view over to one of my large screens and keep the one I'm looking at here, and then I'll have my chat here, and so that I can, you know, try to answer your question quickly. I've told Nick that if I'm not answering a question in the chat, and he's supposed to ping me and there's a question, so he'll be watching that as well. Okay. Alrighty then. So what I'm going to do now is I'm going to go ahead and start with Module 1. Again, the reading assignment on Top Hat and the first 2 homework assignments are complete. It's the slides that are not up, that are not the perfect slides yet, and those should be up this week. And again, I'll have 2 versions. One is the instructor version, which has everything on it, and one is going to be the student version, which has gaps in it. So if you want to download that one ahead of time and follow along, then you can double check on the other one that'll be posted later. Okay. All right. So what I'm going to do now is I'm going to go ahead and share my screen with my iPad here. Let's see. Yes. All right. So you should see something that says Module 1, Structure and Bonding. I need to move my chat over here so I can see it. Go to everyone, and let me go ahead and bring up my panel here. Okay, we have 36 people, and I got most of you on this right here. So, okay. So, organic chemistry. It scares a lot of people, okay? And it's one of those things that is, I like to think of it as a solve the puzzle kind of class, okay? But you have to learn a whole new language, which is all our nomenclature. And so we're going to focus a lot on nomenclature, the structure of nomenclature and such. But then you also have this 3D spatialization, especially when we get into how mechanisms work and why an E2 reaction is a certain way, because you have to have everything kind of aligned just right. So you have basically learning a new language, doing really crazy Minecraft, and then not only that, then I'm going to ask you to say, okay, let's make an alcohol. Then what can you make from the alcohol, and how can you get back? So it's not just a one direction of solving the problem. You have to know that if you use a different reagent, you can get back to where you were. So it's all about kind of, you know, it's mixing those 3 things together. And that really can be a challenge, but I'm hoping to lay things out for you in a nice, logical fashion, so it makes it easier for you to understand the 3D versus the naming versus the going back and forth between functional groups, okay? So let's start with structure and bonding and reminding ourselves about what the atoms are. And in organic chemistry, we're all about the electrons that actually do the bonding and different types of bonding. So let's start talking about that right here. And in this chapter, we're going to talk about where the electrons are in the atoms, and where those electrons are also determines the shape of the molecules, okay? And which electrons we're using tell us what kind of bonds we have, okay? So that's what this entire first section is about. And what you will see is that there's going to be this pattern of electronic configuration versus physical configuration. And doing the comparing the 2, we should see the differences in how molecules are shaped. Okay. So let's start with just atomic orbitals. Okay, can somebody just go ahead and type something in the Zoom chat and make sure that's still working? Everybody's so quiet and serious. I just want to make sure something's happening here. Okay. So, okay, great, perfect. All right. So one of the cool things about atomic orbitals is that because the electrons are moving in this area around the nucleus, And because they have different shapes they can be in and different locations they can be in, we have what we call the uncertainty principle, and the fact that you can observe the location but not necessarily the energy very well, or you can observe the energy but not necessarily the location very well. So what that means is we try to define this into the probability of where that electron might be at any point in time. And that's what we call that uncertainty principle. So it's not that we don't know if there's an electron there or not. It's just we don't know its exact energy or its exact location at the same time. Okay, so because of that, what we can do is we have these things that are called wave functions, okay? And it's a mathematical function that says where the electron might be, okay? When we calculate these based on these different energy levels, we get different shapes, okay? And so our simplest orbital is what we call the s orbital, and it's spherical, okay? And so that is found in each energy level. There is going to be a spherical atomic orbital. And then as we go higher, we can get to more complex orbitals. Once we get to our second energy level, we now can have what we call Ps, okay? And in our Ps, those are those dumbbell-shaped ones, and they have two lobes, right? So it's not necessarily that one is red or one is blue, it's just that there's two possible sides of that nucleus where those electrons can be. But they never actually are in the middle. The electrons never are passing through the center of the atom, and that's a critical thing. So this is just the place where the electrons might be, and they tend to be dumbbell shaped. Now notice there's also an X, Y, and a Z, which means those are three different axes in which we can put those p orbitals such that they do not overlap each other, so that they are taking up three different parts in space. Okay, now once we go up into a higher energy level, once we go up into the 3 energy level, we can then have newer orbitals called d orbitals, and they have much more complex shapes. And then we can actually, if we go to the things like plutonium and stuff, we'll get into the f orbitals. But when we look at organic chemistry, we focus on the s and the p's and the possibility of hybridizing those. We very rarely talk about the d's. Now, things like sulfur and phosphorus will occasionally use d orbitals, and that's why they can actually break the octet rule that we'll be talking about in a little bit. Okay, so if we talk about those orbitals, we have a couple different ways that we can assign a value to each and every electron to make them unique, okay? And that's what we call the quantum numbers. So every single electron will have a total of 4 quantum numbers. The principal quantum number, which tells you its energy level 1, 2, or 3. Then it's the angular momentum one. Okay, the angular momentum is based on the shape. So if you're in the 1, you only have one possible shape, and it's a sphere. If you have a 2, you have a 1, a 0, and a -1. So you end up with 3 possible shapes, and that gives you the p orbitals. Once you go to the d's, that gives you 5 possibles, and f's will give you even a higher number. Then there is a magnetic one. So you can have things that are orbital directions. Every electron, every electric field has a magnetic component, and an electric field component, and a wave component. This is the magnetic component that tells you which direction that magnetic moment in the orbital is. Not which direction the orbital is, which direction the magnetic orbital is. And then of course you can have electrons that are spinned up or spin down, and that's the half or the -half. Okay, so let's talk about what those things look like, okay? So all orbitals start at its lowest energy level, and we start with a 1s. Now, once we get to this next energy level, we have another spherical orbital, which is the 2s. But then we now, because we're in that second energy level, we have that possibility for p orbitals. And we have 3 equivalent in energy places to put electrons. And so those are the 3 p orbitals that can be filled in that second energy level. Now notice, when we go up to the next energy level, the 3, we can start looking at, notice that the gaps between the energy levels are getting smaller and smaller, and we're adding more and more places to put electrons, okay? So we're seeing the gaps increase and the larger number of electrons can be used in each progressing energy level, okay? So the cool thing about that is that, all right, where do I put my electrons? Well, we're gonna learn a rule that allows us to put our electrons in the correct places all the way through all the different possible atoms we can have. Okay, so the first rule we're gonna look at is called the Offbow Principle. And that just means that you're gonna populate the lowest energy first, okay? So if you have one electron right here, you're gonna put it in its lowest energy level first. It'll never go to the second level first. It always fills the lowest energy level. Think of it as filling a glass with water. The water is gonna go to the bottom of the glass and fill from the bottom up. Same thing happens with electrons in these energy levels, okay? Now, the next electron we're gonna put in is actually gonna be spin coupled, one spin up, one spin down, that's spin coupled, and fill the bottom orbital before you fill the second orbital. So that's the Offbow Principle. Always fill from the lowest energy up, even if you have to pair the electrons to do it, okay? Now, a thing to note is that one has a 1/2 spin and one has a -1/2 spin. That's how we can pair those electrons up, because they are equivalent in energy, but they have different spins. Okay. So the second rule we have is we want to take those electrons, and if we have equivalent orbitals, remember we have 3 p orbitals that are all degenerate. That means they have exactly the same energy. So when we have 3 p orbitals that have the same energy, we're going to put one electron in each orbital first. And so what we'll have is, we'll do my pen, one electron here, one electron here, and one electron here. Notice they're all in the same spin state. They're all +1/2 spin state, okay? We're gonna put each of those electrons in, one electron in each of those orbitals until we get to that 4th electron. Once we get to that 4th electron, then we'll have to fill it next. But Hun rule said we have to put one electron in each orbital first, and that they all have to have the same spin, okay? All right, and so that brings us to our next rule here, and that's the exclusion principle. And that means that once we've put one electron in an orbital at one spin, this is a +1/2 spin, the next orbital that goes in that energy level has to be the opposite spin, because we can't have the exact same quantum numbers, which means we have this as a -1/2 right here. So we'll never have 2 electrons that are in the same spin in these orbitals. We'll only have those 1 plus and 1 minus filling that orbital. So with those 3 rules, the Offbow Principle, which means you fill from the bottom up, the Hund rule, which says you have to fill each orbital in each equivalent orbital with 1 electron before pairing them up, and the exclusion principle that says that each has to have a different spin once they fill an orbital, we know that we can make any molecule with the correct number of electrons, and we'll know exactly where the electrons go. Okay. Okay, and we can use the periodic table to help us with this, okay? We don't have to remember how many electrons are in each thing. We can actually look at the periodic table, and that's going to help us see where the different orbitals are and how many electrons should be in each of these orbitals, okay? So if we look at our top row of our periodic table here, we have a total of 2 electrons possible, okay? Our 1s is our lowest energy level, and it's possible of containing 2 electrons and 2 electrons only, which means in hydrogen, which is here, it'll have 1 electron to bond with or share, but helium right here has 2 electrons and has a full s orbital. That's why it's one of those noble gases, because it has a full orbital and it doesn't like to react after that. So let's look at our next row down here. Now we're starting with our next s orbital. That's the first electrons we have, is another spherical orbital. But again, spherical orbitals can only have 2 electrons in them, and we see that here. But then if we go across here, we have a total of 6 more elements here, okay? What that means is we have the possibility for 6 more electrons. And so we have our p orbitals here. And notice there's a total of 6 electrons, which makes it a total of 1, 2, 3 degenerate orbitals where we can put up to 6 electrons in. Okay, so that's our 2p. Now, completely covering all of those is our next level, 3. So we go to our 3, and then we have to fill our 3p, and then we can actually start filling our 3ds at that point. And so as we get to those transition metal elements, we can actually start putting electrons in these d orbitals, and occasionally things like phosphorus and sulfur, which are in this area here. Okay, so we don't have to memorize how many electrons are in each shell. We just have to look at the periodic table and determine where we're going to start filling electrons up. And we fill from the lowest energy level to the highest energy level using our 3 rules. All right, any questions on that? Okay, nothing in the Zoom. Okay. So, using those rules, we can actually draw an electronic structure for each and every element based on looking at it where it is on the periodic table, okay? And so when we do this assignment of electrons, we have to identify which energy level it is, which orbital it is. So energy level would be 1, orbital would be s, so it's the spherical orbital. And we know in the 1s, we only have 2 electrons possible. So if we filled that orbital, we would see that it has a 1s is our lowest energy orbital, spherical, only 2 electrons, so we can put 2 electrons in it. All right, we have more than 2 electrons, let's keep filling, okay? So the next orbital up is our 2s, it's our energy level 2 spherical orbital, and we can put 2 electrons in that, and so we do, right here. The next thing we have is our 2p's, okay? In our 2p, we all have a total of 6 electrons possible with 3 equivalent degenerates. So we have our 2p, which is our px, py, and pz, and we can put 2 electrons in each of these for a total of 6, okay? And in this particular one here, we're adding 1 more electron in this p orbital. I'm sorry, in this s orbital, this next s orbital there. And therefore, by looking at any element on the periodic table, we'll know exactly which orbital those electrons are. So let's go ahead and look back at that periodic table and determine which element that was, okay? So we filled up our 1s's here, then we filled up our 2s and our 2p, and then that gave us 1 electron in this 1s. That means it's this element right here is the electronic structure we just saw, okay? Now, chemists are lazy. So on occasion, what they say is, well, all of these noble elements down here on this side all have full orbitals. So what if we just took the atomic symbol for that noble element, for example, helium or neon? For example, neon would be right here. We have helium, neon, argon right here. And so we just put that we have a full neon shell plus whatever electrons are available. And what we see in our assigning here is that we have that full shell, which is all of these right here, fill that shell, plus 1 more electron to give us that structure for sodium. And this actually turns out, if we look at the periodic table, is what the electronic structure for neutral sodium would be. Okay, so we're following those 3 rules, we're filling from the bottom up, and we're getting to where all of the electrons will be. Okay, let's see, we're at 10:35. Okay. Okay, so what's important about organic chemistry is we want to only deal with the valence electrons. Okay, what I mean by that is we only deal with the electrons in the outermost shell that are not full. So in the noble gases, the helium and the neon and the argon, that has a full shell. Those are not going to bond. But you add another electron to that system, and that electron is the electron that wants to bond. That's the outermost occupied shell that's not full. Those are the ones we're going to make pi bonds out of, sigma bonds out of, and everything. Okay. So how do we find these valence electrons? Well, again, we don't have to memorize for each and every element. We look at the periodic table to tell us where those electrons are. Okay, so what we'll see is, and I'm going to blow this up a little bit right here. Okay, is by looking at our groups, we can see where the valence electrons are. For example, in our, oops, that's not where I want to be. Oh, come on. There we go. All right. In this group right here, all of these in their neutral state have one valence electron because they're in group 1A. Okay. These all have two valence electrons that are available for bonding. Okay. Once we come over here, we have to skip the transition metals. Notice this is row 13, but it's also called 3A. That means boron has 3 valence electrons to play with it. Carbon has 4, nitrogen has 5, oxygen has 6, and fluorine has 7. And all of these are full shells. They have 8 valence electrons, and therefore they don't bond very often. Okay. So what we can see here is that this has 3 valence electrons, 4, 5, 6, and 7. And so that tells us how many times those elements are going to bond, just looking at the periodic table. Okay. There's some outliers here. Boron, which I'll talk about, is kind of a weird one. And then there's sulfur and phosphorus. They actually, because they can use these Ds, can bond more than just the 8 electrons we'll be looking at for almost all the other elements. Okay. So, questions about where to find those electrons, okay? I know some people say memorize it. I say look at the periodic table because you'll always have access to one. And I'm trying to get one on the test. I'm trying to put one at the beginning of the test so you can see it. All right, so now let's talk about chemical bonding we see in organic chemistry. Okay. In organic chemistry, we have 2 types of extreme cases, and this is kind of a spectrum of things. It's not, but we define it as ionic, meaning that one thing has given up its electrons and one thing has accepted electrons to form ions. The other one is covalent, meaning they're sharing those electrons, not necessarily equally, but they're sharing those electrons. And so that's the major difference between ionic bonding is electrons have been given up or accepted, and covalent, they're shared equally or unequally. Okay, and so those are the 2 extremes of the cases that we'll see in organic. Okay, so in the case of ionic bonding, we have it where we started with our molecule, and remember we did the looking at those valence, we looked at the electron structure of sodium, and we saw that it had 1 electron in its 3s orbital, okay? And when we have just 1 electron in an orbital, orbitals are most stable when they are empty, half full, or completely full, okay? That's why noble metals are really, really good. And if we look at the other side of the periodic table, most of those things in group 1 form +1 ions, okay? Because it's easier to give up those electrons than it is to fill that shell some other way. So in the case of ionic bonding, we want to have, if you can make your electronic structure be it such that you have an empty orbital, half full or full, that's going to drive whether or not you make an ion and what kind of ion you make. So in the case of sodium, let me pull this out. Because we only have one electron in our outer shell, it's going to lose that one electron and give us an electronic configuration now that our level 2 here is completely full. It has a total of 8 electrons. That makes sodium +1 happy because it has a full orbital. It has a full 2 energy level, okay? Now, if we look at the electronic structure of chlorine, we see that if we look where it is on the periodic table here, it's on this column here, this number 7 column, meaning that it has a total of 7 electrons in its outer shell. Let me circle it right here. So it has 7 electrons in its outer shell as the neutral chlorine, right? So if we go back to this structure here, that means we have this with a total of 7 electrons here. Now remember, it either wants to be half full, empty, or full. So by accepting an electron, to fill that orbital here, it's going to be happiest. So chlorine forms a -1 ion very readily to fill that shell. Now, interesting that, now we have a full shell and a full shell. We have a +1 and a -1. And this +1 is attracted to the -1, and we can now have an ionic bond, okay? Because electrons were given away and accepted to give us 2 different charges, okay? Okay, so what's the driving force for that? The first driving force is having a half-filled or an empty or a filled one. The second thing is electronegativity, okay? So electronegativity is the ability to an atom to pull electrons toward itself. So if I am more electronegative than something else, I can pull more electrons away from it, okay? So this functions both in ionic bonds and covalent bonds. So let's talk about the scale or the trend of electronegativity. So the most electronegative atom we have is fluorine right here. So electronegativity trends up the periodic table and across the periodic table, with fluorine being the highest one, okay? So, and everything else diminishes from that. So if we look at the difference here, oxygen here, this is about 4, this is about 3.5, this is about 3, this is about 2.5, okay? So it's trending down as we go toward carbon, okay? Now, one of the outliers we have here is hydrogen, okay? One of the reasons hydrogen just can't give its electron away is because it really only has 1. So it seems to have a slightly higher electronegativity than it should, compared with the other things in group 1, okay? But this difference in electronegativity between carbon and hydrogen actually makes a really good bond. And we'll talk about that in a little bit. So electronegativity trends as we go toward fluorine from both sides of the table and diminishes as we go out from it. Okay, and we can use that general trend to control a bunch of different features. It controls hydrogen bonding, it controls polarity, it controls a bunch of these things. We'll go into each and every one of those as we go forward. Okay, so how does electronegativity affect bonding? Okay, so by definition, if the difference between the 2 atoms is less than 0.5, then we consider that a non-polar covalent bond. What that means is they both want electrons about the same amount, okay? So they're both pulling on those electrons about the same amount. Therefore, they have a non-polar bond and they're sharing those electrons equally between those 2 atoms. So that's our first case. Our first case in that spectrum is that non-polar covalent bond. Now, once we get above 0.5 and to around 2, the difference in electronegativity between these 2 atoms, it's still not a big enough difference for one atom to steal the electrons from the other, but it's still pulling electrons toward it. So we have what we call a polar covalent bond. meaning they're still sharing the electrons, but some of the electrons are being pulled toward one of the atoms, and some of the electrons are being pulled away from the other. Okay. Once the difference is greater than 2, then we actually end up having the more electronegative atom steal the electron away from the less electronegative atom, and we end up with an ionic bond. Okay, so those are the 3 definitions for that spectrum of covalent to ionic, and we actually use that excuse me, of that polar covalent bond to give us reactivity. Okay, so let's look at that bond polarity. Okay, excuse my cough. All right, so if we look at 2 fluorine atoms, they both have the same electronegativity, right? They both have the electronegativity of about 4, 3.89, 3.98. So it's about, one has electronegativity of 4, one has electronegativity of 4. They each have 7 electrons in their valence shell. So that means if they share 1 electron with each other, they can make a covalent bond. And because they have the same electronegativity, that's a non-polar covalent bond. Okay, so now each of those atoms has 8 electrons because they're sharing, and they have formed a covalent bond. Okay, so now let's look at fluorine and hydrogen. Hydrogen has an electronegativity of 2.2. Fluorine has an electronegativity of 4, which means it's less than a difference of 2. It's only a difference of 1.8, which means we have a polar covalent bond. And whenever we have a polar covalent bond, we like to show which way the electrons are flowing. And we do that by having this plus side tells us that that's the more electropositive side of the bond, and the electrons are being pulled in the direction of the more electronegative atom. The other way to write that is that we have partially positive on one side of the bond, partially negative on the other side of the bond. Okay, so this is telling us we have a polar but covalent bond because our difference isn't that high. Now, if we move to lithium, lithium has an electronegativity of 1. Fluorine has electronegativity of 4. That's a difference of 3, meaning that the fluorine is going to steal that electron away from lithium, making it a plus charge, and the fluorine is going to be taking that electron away, making it completely transfer that electron here, and we end up with an ionic bond. Notice this is a full positive charge on this side, and this is a full negative charge on this side, and they are electrostatically bound to each other. Okay, so that's where we can find the trend of electronegativity on the periodic table and how that affects the different types of bonds we have in organic chemistry. All right, questions on that? Because it's right around 10:50, I value your time, and so what I'm going to do is I'm going to stop here and answer questions, and then we'll pick up on this on Wednesday. Okay, the lecture slides will be found on Top Hat, but I'm also going to be uploading a set to Canvas for the first few weeks. After everybody has full access to Top Hat and can download them from there, I'm just going to load them to Top Hat at that time. But this set of slides, both the student slides and lecture slides, should be uploaded to Canvas later today. Okay, did that answer your question?
I have a question.
Yes.
For for this slide that says I think it's bond polarity, something like that. So for the fluorine, is that non-polar?
Yeah, the fluorine-fluorine bond is non-polar because they're both pulling electrons the same.
Okay. And then for the last one?
That's ionic.
That's ionic. And why is that?
Because the electronegativity of lithium is only about 1. The electronegativity of fluorine is about 4. So that's a difference of 3. And our borderline is 2, a difference of 2.
Oh, okay.
Has actually stolen the electron away. That's why If you look at the middle one here, it's only partially positive, and here, let me change colors. This is only partially positive, and this is partially negative, meaning it's polar bond. This is a full positive and a full negative, meaning it's an ionic bond. Okay?
Thank you.
And what we'll do is, as you read through the book and do some homework, they'll actually be having you compare the electronegativities, and you'll get to see that, oh, this one's borderline, this one's going to be polar, this one's going to be ionic. Okay? Will we be given a chart to calculate the differences, or must we memorize the values? What we'll see here is that there will be a periodic table, and only in the homework do we have to actually worry about the calculation, and they will give you some values there. For exams for exams, they're going to be different enough. We won't worry about that. But for the exams, I'm trying to find a way to get you a perfect ACS approved periodic table of contents. Okay. So yeah, don't worry about memorizing these things. The general trend will get us most of the way. All right, if there are no more questions, I'm going to go ahead and stop recording. And what it'll happen is